or talk about the quality of that property. So right away we have two terms. One is qualitative and one is quantitative. I want you guys to know these. Quantitative, yes, quantitative. So understand these two words from the viewpoint of engineering. Clear? So quantitative, you are talking about the magnitude, how much. You are talking about the quantity. 1 kilogram of mass, this much volume of water. So all these things, they are related to the quantity aspect, the magnitude aspect. So any property we are discussing, it has to come with a certain number. This much velocity, 5 meters per second. So that speaks of the quantity. Now coming on to the qualitative aspect. So let's say I give you an example of fluid at rest. So the qualitative behavior is that the fluid is at rest. The fluid is moving in a pipe. It's flowing in a pipe, right? So there is a qualitative change, and we are not talking that is it moving with 5 meters per second, is it moving with 1 meters per second. It's not at rest. So there is the actual quality has changed. The actual quality or the qualitative behavior has changed. So these are two important things you must know: the qualitative aspect and quantitative aspect. So what we are generally talking here is, there are two things typically. One is magnitude, of course, which I've already told you, magnitude, and then affiliated with this is like the standard. What standard are we talking of? And this is something which I won't really test you on these things. What kind of standards I'm talking? Like meters per second is what kind of units? SI units, right? There is something known as a CGS, some British kind of system as well. So there are different kind of standards with which you measure quantities. So that comes under the umbrella of quantitative aspect of a fluid characteristic or a property. So in terms of, and these things are generally done for comparison. 5 kilogram is heavier than 1 kilogram. You want to come? Please close the door. So that's the aspect. You want to compare things. That's why you have this quantitative aspect. Qualitative aspect. That means you are talking about the, where is the pen? Okay. The nature. Or let's say the type, and the example stays the same. The flow is at rest, or the fluid is at rest, or is it moving? Clear? So there are some primary quantities which you must kind of know, at least in terms of dimensions. And the moment I start writing, you will realize that it's not that complicated a thing, right? What else? Right. What else could be there? And let's say theta, not to confuse you, but so these are nothing but some basic dimensions. Basic dimensions. So this is one kind of the physical or the basic parameters with which you are going to define the fluid characteristic of the properties. Clear? Why this? Because you have to make a like some foundation. If you have 100 properties and you have 100 different things for everything, for velocity, if you have a unit of V, it's difficult. It's meters per second. Why? Because now you have defined some fundamental quantity. Otherwise, every fluid property would have its own kind of identity, right? It becomes difficult. So to keep things simple, these basic quantities, they are defined. Now there is another kind of system in parallel, which is not, I would say, it's there in the book. So I'll refer to a table as well. Force is F, length is L, and of course time is there. So if you just consider the first three, most of the quantities, they can be identified as MLTs, and in this case FLT, and F is in fact right, something like this. This is kind of an equal sign here. Why this? Because if you're doing certain analysis, let's say the force is very dominant, it comes most of the time, so rather than writing MLT minus 2 all the time, you say that okay, F is a basic quantity, and then you do your analysis based on this. So table 1.1, and let me write it way up clear, at least in 4th edition. I'm not sure if somebody has any other edition, please check. It is the first table, and there are a bunch of quantities, those fluid properties, characteristics, they are written on the left. Viscosity is there, the density is there. So all these different parameters or these properties associated with fluids, they are listed. And alongside with that is like MLTs and the corresponding FLTs. And I want you guys to kind of know that table by heart. I know it seems ridiculous, but that's the way it is, right? Because the moment you know of any term, let's say viscosity, dynamic viscosity, in order to characterize that, actually what is it? Does it have a mass in it? Is it associated with time? You should know that component, which are typically the dimension aspect of it. Let me ask you some basic things. Let's get some examples here. Acceleration. Does it have mass in it? Right? Good. Few people are getting excited. Let me go for some other one. Energy. Give me in this kind of format. Right? And you put F like this, and then you can crisscross certain things and you can do it. Yep. Okay, so we go to the next slide. Let's see. We keep it, and we go here and here, and then we go back here. Yep. Okay, so there is something known as dimensional it's not that hard as compared to the name given to this aspect. All theoretically derived. By the way, my handwriting is not that bad, but whatever is appearing here. All theoretically derived equations are, let's say DH, and I put that, I don't want to write it again, DH, dimensionally homogeneous. That is to say that on left hand side the thing is, the units, if you kind of cancel the units on one side and then look at the left hand side as well, the units come out, should be the same. If I write Force is equal to velocity times area. Is it good or bad? Right? It's wrong. So if I ask you these kind of questions and true or false in the exam, you should be able to do it. And I already told you guys the rule for doing true false. Did I? Yeah, that's the dilemma of teaching two sections. Sometimes you think you have already told something, which is kind of important. So there are certain things, the moment you read a true false statement, you say, oh, it's true. Something like this, oh, it's false. But there are certain statements which confuse you. Clear? And you are not sure what to do. So the rule which works most of the time is that think hard, read the statement about 10 times, and once you are convinced that it is true, write false. And if you are convinced it is false, write T. So you will get a point. That this works, right? So try this and hopefully you will get some extra points. So having said that, let's put it back. By the way, I think in FM2 some people can bear with me. I had negative marking as well. Did I? Anybody who took FM2 with me and is here? No? He's not here? Okay, anyways. So my point is, if things are very simple, right? If true false, they are generally straightforward things, and just don't go TFF or try to find a pattern, like it could be TFF, 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 FFT. So rather than doing this, if you do wrong, then there's there might be a negative 50%. Right? So that might be a possibility, but it's not the time right now to talk of these things. So moving further, if you, I would strongly recommend you go over some of the sections which talk about different units, CGS, SI. Right? This is not the right forum to go into the details. I'm sure you might have covered all these things much before than that. So rather than doing the same story again, I would encourage you guys to go over it. And let's go over some definitions first, which is measurements of fluid mass and let's say weight. So the first thing is density, which is mass per unit volume. Clear? Everybody knows density is mass per unit volume, and there are certain symbols in different standards. And next thing is the specific weight, which is given as, by the way, the symbol is this. This is rho. This is gamma is rho times G. Again, look for the right units. Specific gravity given as SG. Do you know what is the specific gravity? Anybody? It's weight per unit volume. Any other wild guess? It's a ratio of density of any fluid with respect to water at 4 degrees Celsius. So what should be the units here? Good, no units. Okay, next. next thing is ideal gas law, and this is P equals yeah, and also comes in if you are talking of some other number of moles kind of things, those details. But again, it's such a simple thing that I don't want to go into the details over here. By the way, if I ask you, generally I don't ask numericals such as I give you 3 variables and ask you about the 4th one, right? I give you 5 variables and ask about the 6th one, and you just plug in numbers and move things right and left. You have already cleared your FSC level, so I don't expect you, I want you guys to go beyond it. So if there is any concept which is involved in solving a numerical, I would go for that. And you have to think and then do it. It's not number crunching on a calculator. Okay? So some of the questions or the examples which you see in the book, most of them they kind of do number crunching, especially some examples. But you might go for that as well. But I would really go after concepts. You should know the concept. And one more thing is, whatever I cover in the class, I go back and I make questions. So I'm fresh, whatever I have taught you. For example, Knudsen number, as I have already told you, just to be on record, it's not given in the book, but that is, in order to understand continuum hypothesis, it is important you understand what is a Knudsen number. That's why I discovered. Then I have the authority, if I've covered something in the class, I have the authority to ask in the exam as well. Right? So similarly, I would strongly encourage you to pay attention whatever I am teaching. If somebody asks a question that I digress, then that digression is also part of the curriculum. Right. Any question? You have a question? Okay. Stretching? Feels good? Yeah. Okay. Another property, a very interesting property, is viscosity. Any idea? A wild guess. You might have heard of it. Yeah, I guess everybody's right. One by one. It's a very good definition. Right at the, I don't have to cover so many things now. Nothing else. Right? Friction between different layers of fluids. Anyways, intuitively, I mean, common sense tells you that if you have a glass of water and some honey poured in a jar, if you try to pour water, it just flows right away. And if you try to do this the same thing with honey, it takes a while. So that means there is some fluid property which is different, right? It is, for one fluid, it is much easier to flow, and for the other one, it is harder. And if it does not flow, what is it? It's a solid. Because the fundamental thing which we said was what? Difference between in terms of the definition of a fluid, the key word. Okay, if you can apply shearing force on a solid as well. Right. It flows continuously. The continuous deformation. So the key word is continuously. That is very important. Because you can always deform a solid as well. You apply a force, it can deform, and if you leave it, either it comes back or stays there. So that is either elastic deformation or plastic deformation. If you are studying mechanics of material, you might encounter these terms as well. You already did? Okay. Anyways, the key word in the definition of a fluid is continuous deformation. Okay, so what we have is viscosity. So in layman language, I would call it the fluidity. which is given in your book as well. I'm putting these quotes because I think it's not a legitimate word. If you try to find it in Oxford or a Cambridge dictionary, you won't find it. But fluidity means how much easier for it to flow. The kind of fluidity involved in that particular fluid which we are talking about. So there are different layers as suggested by somebody. Just to give you an example, if there are two plates, right, and let's say if there is solid in the middle, and you start to apply a force, let's say P, would this cause a normal stress or a shear stress? Shear, right? It's in this tangential direction. This force will cause a shearing stress. And now let's say if this solid is permanently attached to this plate, what will happen? The whole solid body would move, right? Either if it is not attached, then maybe the top plate would move and nothing happens to the solid. But this is not a very good example, but let's move and put a solid, and instead of a solid, put a liquid there. Let's see, eraser. Oh, good. This, okay. Now let's say there is a fluid in there. Now there is a property of fluid which says that it sticks with a solid boundary. It sticks with a solid boundary. So we have two plates. One is at rest. This is at rest. So let's say there is a fluid particle here, and there is a fluid particle here. And with this force, what happens is it moves with a velocity u in this direction. And let's say, to give you an example, this is like 1. Right? Now what is happening is, you are moving the upper plate with a velocity of 1. This plate is not moving. So due to this property, which is known as the no slip condition, it's a no slip condition. Let's write it. It's a no slip condition, right? So what causes, due to this no slip condition, the velocity at this point is 0, and velocity at this point is 1. Now since between these 2 points you have fluid, and the fluid initially was at rest. It's not coming from there, by the way. It's not coming from this side. It's not coming from there, right? So the moment this plate moves, what is going to happen is the next layer, which is just below it, it would also start to move. If this is moving with u is equal to 1, the next plate would, the next layer would also get the effect, right? So let me do one thing as well. That's my instructor used to do to keep few students awake. So 32B, right? Is GC Wasim here? Wasim, yeah. So what do you think? What should happen? The layer which is below this one, should it move faster or should it move slower? Sorry, say it loud. Okay, good. So if this is, let's say, u is equal to 1, what should it be? 1.1 or let's say 0.9? Okay, so you expect the velocity of the next layer to be a little less, right? Why? Because there is some friction. That friction kind of drags the next layer, but that drag is a little lesser. So the upper layer is moving with a higher velocity, and the lower is moving with a different velocity. But again, right in the very first lecture, I also said that there is a microscopic level and there is a macroscopic level. There are two different levels to see things. So if you have a microscopic level, what in fact is happening is the molecules, they are moving upwards, downwards, right, back, left, everywhere, right, which is known as like a Brownian motion also. They are randomly moving, but the overall aspect is that they are moving to the right as well, right? So one layer is moving at a higher speed, and then the lower one is moving with a slower. Clear so far? So now mathematically you want to model that aspect, or in terms of a fluid property you want to model that frictional effect. That frictional effect is modeled as viscosity. That's the physical significance, what is happening. By definition things are very easy. Mu is this, or viscosity, which is this, the symbol is this. It is always easy, mu is equal to this. But most important thing is that you should develop some key concepts right in the beginning. This mu is in fact modeling the frictional effects between layers. That's what, that if it is high, that means the layers in honey, they have a lot of friction in between them, and the friction is much less as compared to honey in water. So in water things are different. So mu is less, and to be precise, this is known as dynamic viscosity. Dynamic viscosity. Anyways, so we were talking about different layers. So let's say the next layer has some other velocity, and this one and this one and that. And if I join these points, let's say like this, and this is here. What do you think this is? What? Right, this is one thing. And let's say after a while the particle is here. So you have a similar line here. Right? So if I ask you that the velocity u, let's say if it was 0.7 here, this is same as 0.7 here. Is the velocity changing with respect to x? If I write partial u, partial x, what is it? Are you sure? Now you are sure, right? So the velocity is not changing in x direction. Mathematically, what does that mean? Partial u, partial x is 0. Why did I put partial sign? It's 1x is good. It's one component of velocity, and u is in fact dependent on x and how many variables? There are two independent variables. Had it been only like a one-dimensional thing and there is no second dimension, I could have written du by dx. There's some kind of mathematics involved as well. Okay, so next is in line is Tehmas. Did I say it right? Okay. What is this? What should I write here? Is this good enough? Is it 0? You are saying yes. Is this the final answer? Should I lock it? You lose. So you get 0. Anyways, partial u, partial y. If you look at this curve, so is the velocity changing in y direction? Right? So there is something known as gradient. In mathematics, you learn that there is something known as gradient. Let me draw it here. And most of the time, if this is like this, you say that this is the slope or this is the gradient. And typically this is x, this is y, so you write dy by dx. Clear? So that's apart from doing fluid mechanics here, I also want you to see the relationship between mathematics and whatever we are studying. There's a very strong, if these things, they are two different subjects for you, it's not good. Try to bring these things close together. It's all applied mathematics. So develop some basic concepts right now, and it would be helpful for you guys later on. So if this is dy by dx, which is the slope, over here we have u here and y here, and this curve, which is something like this, it has a slope as well, right? And this is kind of 0 here. So partial u, partial y, you are not looking at the slope from this point of view, you are looking at a different viewpoint, but still it is a slope. So partial u, partial y is the gradient, which is the slope, how u changes in y direction. And this term in fluid mechanics is typically known as the profile, the velocity profile. Okay, so Abdul Samad, I need to take a roll call. Yeah. Etisam. Okay, so we already talked of a linear thing. This is one plate and this is another one, and these things are moving like this. Do they always change linearly? Means if this is one and by the time this is changing, is this always linear? Should it be always linear? Could there be any other profile, technically speaking? Means it may happen that the top layers, they are changing differently, and then they are changing differently, and by the time you are very close to the lower plate, things might change differently. Because gradient is nothing but the rate of the way things change with respect to something else. I didn't say the word rate, because rate is typically involves time. Partial u, partial y, there is no density right now. You're right, if density might be a factor, but what I'm asking is it always linear? Yes, no. How many for yes? People are looking around and pulling down their hands. Majority rules. Democracy. No, it's not always linear. It's basically the kind of fluids which are involved, plus the kind of pressure differences that might occur. So sometimes this is linear, and sometimes it happens like this. So if I ask you, what kind of shape is this? So one possibility is parabolic profile, which means u is changing as y square, right? It's kind of this. It's proportional to y square. But it is not always necessary that it changes like parabola. It could be any other thing. It could be any other function. Let's go with, it could be this one as well. And if you see, maybe it is y raised to the power 7.8, whatever. You can fit in the curve, but my point is these profiles could be very different. Clear? So the next thing is, let's go, I don't know, I should have a better way to switch slides. Harmagan. Okay, you tell me that we applied a force, and what causes the fluid to deform? What kind of stress? Sorry? Yeah, shear stress. So shear stress tau. So that shear stress which is being caused between different layers is directly proportional to the velocity profile. And if I have to put an equal sign, Basit is here. So what should I do? I should put a constant, and that constant is good. I like that. And this is known as dynamic viscosity, which is the constant of proportionality. Now that tells you how the layers would move, how much friction is there. So that kind of governs a relationship between the velocity profile and the shearing stress. So far so good? Okay. Now if I ask you that what kind of relationship is this? It's direct. No, that's okay. If you remember in the last slide, let's say I put this is not alpha. So what was the name? This is good. And what is the other name? If it is, let's say, y cube or y 3.1. If this is linear, what is this? Right. So this is most of the problems in the world are non-linear. It's not a graduate level class, but if I were to teach a graduate level class, and I also give this example because once I was learning dynamics, there's some linear and non-linearity involved in it. So one of my instructors gave me this example, so let me share. It's a couple of minutes. All those guys who are sleeping, let them sleep for a while, and I'll tell you a story. Just to signify the difference between these two linear and non-linear worlds. So let's say that you are sleeping, right? And then the moment you wake up, you realize that you have been abducted by Mauritians. How many of you know what is a Mauritian? What is that? Aliens from Mars. Yes. And you realize that those funny creatures, they have abducted you and they have taken you to Mars. And before you say anything, they start beating you. And their leader comes in and he asks you a question. And he tells you that if you answer it correctly, we'll let you go, else you are here for the rest of your life. And he asks you, what is an animal? Because they might want to invade Earth, they are getting information about Earth. So they ask you, what is an animal? And since you got the beating of your life, you say elephant. Right? Is it the wrong answer? It's a good answer, right? And they go back and they do some research and they put a telescope and they look at Africa maybe, and they find a big creature, and you describe what is an elephant, and they see a big creature like that, and they are happy and they let you go back. So you are back at your home. So the point here is, Is elephant an animal? Yes. Is it the only animal? How many species did you miss? Right? So in the world, if I say most of the problems, they are non-linear. That means animals. And the problems which are linear, they're big, huge problem, like elephants. But that is not the only problem. Most of the physical phenomena, they are non-linear. They are not linear. We kind of generally study linear problems to get by, and once you go for your higher education, you study non-linear problems as well. So you can see the difference if you just make elephant as an animal, and that's the only animal. So that is a very wrong assumption of thinking. So a big difference, if right away you want to visualize that what is linear and what are non-linear problems, so you can well imagine the difference between the two. There are problems which can be treated linearly, and one of them is right here in front of you. So the problems which are linear, that means if the stress is directly proportional with partial u, partial y, that is to say the power is 1, it is linear, and we call these fluids as Newtonian fluids. And what could be the other category of Newtonian fluids if it is not 1? Good. People are picking up things. I'm glad. This thing is kind of working. Non-Newtonian fluids. And could be anything. It's not only integer. If it is generally 1, 2, 3, 4, or it could be 1.2, 1.3, and these kind of fluids which are generally following this law, they are, I think, power law fluids, and known as power law fluids. But for this class, we will stick to this one. And as an engineers, in order to solve most of the problems, we treat fluids as Newtonian fluids. In fact, most of them, they do behave. By the way, blood is what? Newtonian, non-Newtonian? Wild guess. Non-Newtonian. There are reasons to it. But in order to simplify some analysis, you treat it as Newtonian. But next time you go to a doctor, and if you have some kind of do something with the blood, ask him, Newtonian, non-Newtonian, which blood I am getting. So make sure you get a non-Newtonian fluid, blood, right? Next thing, and now you should be able to clearly differentiate what is the difference between these two, Newtonian, non-Newtonian. It's a good point. Just let me couple of things, and then we'll have a small break. And show. We keep this. Shear. Okay, if the shear rate increases, the apparent viscosity decreases. So these things are known as shear thinning fluid. Apparent because as long as in actual world the fluid has its own viscosity, but the moment you apply some shear on it, the apparent viscosity changes. So that's why they are known as shear thinning. Again, we are not going to go into details. If it is the shear thinning, Hamza Ahmed, what do you think I should write? If one is thin, the other is? How many Hamzas are there, by the way? Shear thickening. So if shear rate increases, the apparent viscosity also increases, right? And there is something known as on day one I gave you an example of toothpaste. There are certain fluids which you are not sure whether they are solid or they are fluids. So I also said that it depends on the shear stress. If it crosses a critical value, then it starts to behave as fluids, otherwise they are treated as solids. So those kind of substances, they are known as this, right? And we also said that rheology is kind of the area which covers these kind of things. Again, we are not going to discuss these things in detail. So let's have a break of a few minutes, and then once you come back, we will have the attendance and we'll continue moving forward. Okay. Thank you.
x, let's say this is x equals 1, x1 is, let's say, 0 here. I'm giving you a very kind of FSE or even matriculation kind of solution here. u2 minus u1, x2 minus x1, x2 minus x1 is 1. What is 0.5 minus 0.5? That's why partial u partial x is 0. That means the fluid velocity is not changing in this direction. It is not changing in this direction. It is not changing. All of them, they are x directions. Right? But once it comes to the y-axis, which is this one, right? The velocity here is, let's say, 0.2. Velocity here is 0.7. And the velocity on the top is u is equal to 1. It's not linear. Let's say it's some if I join all these lines with this magnitude, maybe the thing which is confusing you is this is y, this is u. Let's say if there is something like this, that means at this point, what is, let's say this is the height 1.0, this is 0. What is the velocity here? The value of u is 0, and we already know that this is 1.0, the velocity. So these are nothing but the values of u. Since it is very close, it might be 0.99. Over here it could be 0.8. Over here it could be let's say 5. Over here it is, let's say 0.2. Something like this. So now the velocity is varying, and partial u, partial y, if you want to measure it, it has some number to it. Why? Because you are looking at this change, you are looking at this change, that change. If it is parabolic, that means it is changing with respect to y square. U is changing with respect to y square. So partial u, partial y is like linear. If the profile is parabolic, this is called parabolic profile. If u is changing with respect to just y, which means linear profile, what is partial u, partial y? It's a constant. That's why the gradients for, let's say, this is a constant gradient, constant slope. The slope is changing. Just go back and plot y is equal to x square and plot dy by dx. Plot dy by dx, it is 2 times x. As you change x, the slope will change. Use the mathematics. So somebody also asked about like molecule level. You are not, because the molecules, they are constantly moving. Molecules, they are moving down, they are moving up. So the molecules, we are not talking of molecule level. We are talking of a macro level, where if this is a fluid particle, it goes straight. If we are talking of a fluid particle, it goes straight. We are talking of fluid particle. So far so good. Any question?
Oh, this is one case. We are considering a case. Yeah, so the stickiness is coming due to the no slip condition. A no slip condition. That tells you, let me write it. That tells you if this is the condition, it means the layer of fluid which is exactly very close to the solid, they have the same velocity. That's exactly the same velocity. No slip condition. Clear? Next thing, we already studied this number. Now the next thing is this one was, so RE is abbreviation of Reynolds number, and this is one of my favorite, because if anybody who wants to pursue his degree, especially later on in fluid mechanics, this is something which you encounter a lot, right? Reynolds number. So what is it? Let me write the definition and then I'll explain the physical significance, because at times it is much easier to just go over the mathematical version. Oh, that's a number, lambda over L. What is lambda? It's a molecular length scale, that's it. The physical significance, it's very important. It's very easy to just memorize and then it's a matter of time, you just forget it. But if you develop the approach of understanding the physical significance, that really helps. So let's write the definition first. And you will encounter a lot later on in chapter 6, I guess. So as of now, it's a ratio of inertial forces to viscous forces. So this is the definition. Density times U times L over dynamic or absolute viscosity. Now we know that density is rho, that is a property of a fluid. Viscosity is also a property of fluid. Now U and L, last time what we studied different scales. We said in order to measure something, we have a characteristic scale. So if in case of Knudsen number, we had different length scales, and they were defined by lambda, lowercase l and uppercase L. So this L is exactly the same L, which is the characteristic flow length. So if you are measuring any flow past a wing, let's say, so the chord length could be the characteristic length. Similarly, if you are analyzing flow in a pipe, the diameter of a pipe or the length of the pipe could be the characteristic length, and it's up to you guys. Once you are doing research or analysis or experiments, then you choose that characteristic length, right? And these numbers, they are dimensionless. So if you plug in units, you should not get any unit associated with the Reynolds number, because it is a ratio as well. A ratio between inertial force, which is a force, over viscous force, which is still a force. So forces, they cancel out, right? Now what is U? It is a characteristic velocity. It is a characteristic velocity, which also tells you that once you are doing experiment, let's say the incoming velocity of the car which you are driving. So all these things you set right in the beginning, some characteristics, so that once you non-dimensionalize with respect to that velocity, it's much easier to understand things. Clear? Now, let's say as an engineer, what happens is you have been given a task to analyze the flow and to compute the lift on an aircraft which is flying at 40,000 feet, right? You have given this task to compute the lift or the flow pattern or whatever analysis on a flying aircraft at an altitude of 40,000 feet. So one way is you grab hold of a pilot and you say, let's go up in the air and do some experiments. He would ask you why. Oh, I'm just testing the aircraft if it is safe or not, or I'm trying to see if the design is good or not. He won't go with you, right? Because then he would say, oh, these things are not tested for the aircraft, right? Why should I fly it then? But the point here is, once especially you are in the design phase and you have to do some measurements at a larger scale, like in an actual condition, you want that those parameters can be computed right in your lab, right? You can do some laboratory experiments and get the same results as you would have gotten if you are flying at an altitude of 40,000 feet. So there has to be some comparative relationship between those two scenarios, right? There has to be something which is being matched, and then if you say the coefficient of lift on this model which you are doing experiments in the lab is exactly the same as the lift of an aircraft. So there are two different cases now, and there is something which relates these two cases. Let's say, where am I? So let's say if let's say if I don't make a duck sort of a thing, right? So it's kind of an aircraft, something like this, and then you have a model, right? So let's make a star or something like this for the glory of the country, right? So there is rho 1, there is u1, there is l1, and there is mu1, and this is your lab. Let's say ECR. You're sitting here and it has its own rho 2, let's say u2. Now these are the conditions which you are given as design engineers. So at 40,000 altitude, 40,000 feet, you have to compute certain things on this aircraft, right? So at 40,000 altitude, the density is given. You already know what is the density of air there. You already know what is the viscosity of air there. So that is also, so those two, for example, those two parameters are fixed. So this is fixed and this is fixed. And the characteristic length, you decide, okay, I'll take the chord length or the width of the aircraft, which is this. U1 is the speed with which aircraft is flying. So you have been given a task that if the aircraft is flying at U1, which may be 200 knots, give me this. So you already know that the velocity with which the air is coming with respect to aircraft is like U1. People might say that, okay, aircraft is it stationary up in the air? No. If there is no gust, there is no other problem, then the aircraft is flying, so it is as if the wind is coming with the same velocity. Okay, now here comes your model, which is exactly of the same kind of pattern. I just drew it differently so that you know this is a model. Let's say it is like a 1:48 scale kind of thing. That means if your length of this is 1 meters, let's say 2 meters, so the length of this L2 is like what? Something like this, right? Something like this. So now, do you know there is something known as a wind tunnel? How many of you know that? There is something known as a wind tunnel. No gentleman cadet knows about a wind tunnel. No GC. Are you dead sure? You don't know, or who cares? Okay. You should spend a night there, I guess. Then you would know. Anyways, wind tunnel is something where you do experiments. You simulate the flow is coming in. It's like a closed chamber, like a test section. You put a model, and then with the help of pumps, you drive the air on top of it, and all these blah blah stuff. right? Anyways, so few people, they do not even want to know about what is a wind tunnel, but let's say those who already know what is a wind tunnel, you do generally experiments, especially for aircrafts or missiles. Okay, so now the thing is, you have that wind tunnel in this room. You already know what is this. This is nothing. And what is this? And once you have already manufactured your model, you are already knowing what is this, right? So in order to match the two cases, case 1 which is the actual aircraft, case 2 which is your model and you are doing experiments in the wind tunnel here, what you need to do is match the two Reynolds number. You have to match the two Reynolds number. So in the wind tunnel, you can always change the incoming velocity with the help of converging divergent nozzles. If somebody is interested, they would study later on. But the thing is, like a Bernoulli's equation, if let's say this is 10 meters per second here, is it higher or lesser? Let's say 20. Is it always higher? That sure? Let's say it is 20. I'll write this as well, for example. Okay, this is true for subsonic flows. This is true for subsonic cases. Subsonic means if you are less than the speed of sound. So people who know what is supersonic, and people might get supersonic over the weekends. So all those who are supersonic kind of guys, they would know that then the velocity does not increase, rather it decreases. Anyway, this is not the part of the course, it just popped up. So, but the point here is, these two quantities, if you match it, then you can talk that the two cases are comparative. The lift being produced on a model is the lift produced on the actual aircraft, as long as you make sure that this is happening. One Reynolds number is equal to the Reynolds number in your wind tunnel, right? So that is kind of interesting. So that these numbers or these analysis of matching, they help you a lot. That's something interesting. And expect these kind of things in your exam as well. If I happen to take a quiz sometime soon and I ask you something on this, and don't say that, oh, actually factually this happened, that happened, right? So you should, if you have any question about this, please shoot out right now. Questions? No questions? Crystal? Okay. Okay, next thing is compressibility of fluids. Are fluids compressible? Yes, no, no, yes. It depends which kind of fluid are we talking about. Is it water? Is it air? Sorry? Okay. So let's write, there's few things which are important in this aspect. Bulk modulus, defined as E sub V is dP okay, so dP is differential change in pressure It's a differential change in volume. Volume, just V with a line is volume. So for velocity, generally I don't put this bar. So if at any stage there is a confusion, please do ask if there is any query about it. Similarly, if it's straightforward that how do you go from this to this density thing, right? And once I'll give you an example, things would be a little clearer that how much compressibility is allowed in terms of let's say water. There's an example in your book. What is the pressure? What is the pressure at right now? Let's say approximately. Sorry, 1 atmosphere. That's a good answer. In terms of PSI, pound per square inch. So there is atmospheric. P is approximately 14.7 psi. I just took the other sections class today, and since I kind of discussed it, let's talk with you guys as well. How many of you know swimming? Good swimmers? Average? Say good. I'm not going to take an exam, right, or test you. So you can say like, oh, the next person who is better than me is Phelps, right? I'm the second one. So you can always say that. Anyways, let's say this is sea level and the pressure is 14.7, and there you are with the flaps front, right? Yeah, freestyle. And the pressure, if you're right here, the pressure is somewhat like 14.7. Anybody who has done no, frogman kind of scuba diving, GC? No? It's in PMA, not here? Okay. Do it. It's interesting. It is very interesting. So, sorry? What is it like? You have to experience it, unfortunately. But learn swimming and go deep, like in the swimming pool. If you come up alive, you can tell the experience. Right, otherwise the person who is a lifeguard, he'll tell the story. That the instructor of fluid mechanics told them to go down. Okay, so what I was referring to is so by the time you are like 10 meters in water, if you are 10 meters in water, this pressure, let's say if it is P, it becomes 2 times P. So the pressure at sea level is the water, the column of air on you, is that weight of that air which you are experiencing. But the moment you kind of dive at this level, now there is this pressure due to the column of water which is on you. So you start to experience few things. This is 2 times the pressure, the sea level. And similarly, if you go down like this level, 3 times P. And this is like 60 feet, 20 meters is almost 60 feet. So if you guys get a chance to go for that course, what they do is they put you in a capsule kind of thing and they start to increase the pressure. They try to simulate a situation as if you are underwater. Right? They want to test you that physically can you handle that much, like 10 feet, 20 feet, I don't remember it, but then there's a gauge as well, and they are looking at you through a window or a camera that what is happening. So some of the people, those who cannot do it due to that pressure, they get what? Bleeding from ear, nose. So it's tough sometimes. Most of the time people get through, but sometimes you never know. Right? You never know. So they just want to clarify that okay, everybody is fit enough to do this course. But I'm trying to stress here is that this 2 times pressure is huge. 3 times, again, you start to feel something. All those who are good swimmers just go like 15 feet and there you go. You start to feel these small bumps in your ears and you kind of get stressed. So in order to, these are numbers given in the book as well. If you want to compress, we have to write, compress 1% of a unit volume of water, that requires at 60 degree, that requires 3120 psi. A lot of pressure, right? So the amount of pressure you require to compress water is too big a pressure. Still you can compress it, but generally if you assume that it is incompressible, that's fairly a good thing to assume. So the example which I gave you was just to give you a feel that 3120 is a very high pressure. Clear? Okay, so the next. Okay, time is up, so we'll continue this. Attendance. You're done? Close कर दिए?